Morning, welcome back. We are going to start our second day in the cosmology lecture. So, Professor Carlos, feel free to start.
Yes, hello again, everyone. I hope you had a chance of seeing the first Euclid images. They were just publicly released half an hour ago. If you haven't seen them, I can post a link on the Discord channel after the class, a link where you can see them. They're really impressive. They're definitely worth having a look at. So yesterday we discussed a little bit the theoretical framework for the kinds of tests we want to do, and we also started talking a little bit more specifically about this idea of varying fundamental constants, and we ended by discussing a possible classification of these fundamental constants. So just to connect what we said yesterday, so here's a bit more motivation for these kinds of studies. Um, in most extensions of the standard model, you have additional space-time dimensions. And one of the things that occurs in these models is that the quantities that are the real fundamental constants of nature are not defined in our 3+1 dimensional space. They are defined in the higher dimensions. And the things that we perceived in our 3+1 dimensions as constants, they become just effective quantities. And there is, again, no reason to expect that they should be really constants. And if you think just in terms of dimensional analysis, how would you relate your 3+1 dimensional constants to the true constants in other dimensions? You can more or less easily see that the differences in terms of dimensional analysis would be factors of with units of length to some power, and the typical sizes would be just characteristic sizes of extra dimensions. Now, as the universe is expanding, the characteristic sizes of these extra dimensions should change, and therefore you should also expect that these effective quantities in 3+1 dimensions should change at some level. Again, these things they depend on three parameters. You don't know if these parameters are large or small, so we don't know if the effect is going to be big and easy to detect or just tiny and difficult to detect. But these variations should be there. And again, to give one specific example, I think I mentioned this yesterday, in string theory, a varying alpha, a varying fundamental constant, is unavoidable at some level. For those of you interested in specific models and in particular in particle physics connections, you can see how these variations emerge in Lutz-Klein models, in superstring theories, brain world scenarios, and so on. And the slide, you have some possible references that you can use to look into this in more detail later on if you want. But that is not exactly what we want to do. What we want to do is to test it observationally or local tests. So just before getting to that, let me just mention one more thing, which I didn't mention yesterday, which might be useful for you to keep in mind. And this has to do with the role of constants in our physical theories. There's essentially two different schools of thought, and you can think about your own view of physics, and you can think on what side of this divide you can place yourself, or which one you find the most appealing. So one school of thought says that these constants are kind of signposts for asymptotic states or for the emergence of new phenomena. So for example, you can think of the speed of light as the limiting velocity of a mass particle in flat space-time, or in other words, this tells you that as you get to speeds close to the speed of light, you start seeing things we call relativistic effects. So just a way of telling you how close you are to physical settings where these effects will play a role. Equally, you can think of Planck's constant as a limiting uncertainty. You can think of Newton's gravitational constant as the limiting potential of a mass which doesn't form a black hole, because if you start with a certain mass distribution and keep increasing g, eventually that mass will collapse and form a black hole and so on. So for each sector of physics, you should have one of these constants telling you when new and interesting effects would emerge. So that is one school of thought. The opposite school of thought is to think of them as merely conversion factors. So this is essentially the school of thought that you're subscribing to when you are doing complicated analytical calculations and you decide to make your life easier by setting the speed of light equals 1, for example. So in principle, you are free to do that. And of course, it makes your life easy. It simplifies your calculations. But by doing that, you're kind of buying the idea that these are just conversion factors and therefore you can give them any values you want. And that is true to some extent, but it's not completely true. Uh, because if you think about it, you can choose to work in units where the electron charge, the speed of light, and Newton's constant are 1. That's perfectly fine. But you cannot work in units where speed of light, the electric charge, and Planck's constant are 1. Because if you did those, then the value of the fine structure constant, which is a dimensionless number, and which is a combination of the three, would not be the 1 over 137, which is a value it has in our universe. So the point here is that you have some freedom to redefine these constants, but you don't have complete freedom because numbers are numbers, dimensionless quantities are things that anyone can measure, and they should be the same and have the same value in any system of units, in every frame, and so on. So therefore, this takes us to another question which you can ask, which is how many of these fundamental constants are really fundamental? Um, and as far as we know, with the physics we know today, and with the physics that is tested and well established, the answer is three. So you need to define a unit of length, a unit of time, and a unit of energy. And if you've done those, so if you specified your clock, your ruler, and your weighing scale, then all your physics in the sense is defined. Um, you may be aware that there's something called the International System of Units, which conventionally has 7 fundamental units. Uh, that's partially for historical and conventional reasons, but if you think a little bit, you can see that you don't really need 7. So, for example, in the International System of Units, there is a fundamental unit for temperature, but temperature is just a peculiar way of measuring energy. So if you have a unit for energy, you don't need really an additional unit for temperature. So that's just a side note, but it's something that might be useful for you to keep in mind while we discuss some of these things. Um, and let me start, so getting into more practical details by illustrating how some of these constants affect the universe as a whole. Some some cosmologists and particle physicists like to discuss what we call counterfactual universes. How would the universe be different if some of these couplings changed? Just like historians uh, like to think of counterfactual history. You know, what how would history be different if Napoleon had won Battle of Waterloo or these kinds of things? Um, so let's take the fine structure constant, which is a measure of the strength of the electromagnetic interaction. So it's 1 over 137 approximately. And also take the analogous quantity, so the analogous dimensionless number for the strong interaction, which is about 1 over 10. So if we increase alpha electromagnetic by about 4%, in other words, if we make electromagnetism 4% stronger than it is, or if we reduce the strong force by 0.4%, then a very important carbon resonance, known as oil resonance, would not exist anymore. And one of the consequences of this is that stars would not produce a significant amount of carbon anymore. And therefore, carbon based life forms like us would not be around. On the other hand, if you go in the other direction, if you decrease the strength of electromagnetism by 4%, or you increase the strength of the strong nuclear force by 0.4%, then stars would not produce oxygen anymore. So it's actually interesting that there's only a very narrow range of strengths of the electromagnetic and the strong interaction for which stars produce simultaneously significant amounts of carbon and of oxygen. It's relatively easy to produce one of them but not produce the other. Only in a very narrow range of values of these couplings can you really produce significant amounts. And we're only talking about percent level variations of these quantities. We're not talking about orders of magnitude difference. So these things are actually very sensitive to the value of this coupling. And just to give you a couple of other examples which I find interesting, if we increase the strong nuclear force by a bit more, by about 4%, or decrease it by 10%, then we would have what we sometimes call the diproton disaster. So helium-2, so a nucleus of helium just with two protons without neutrons, would be stable. And then all the nuclear fusion reactions that we know in stars would be amazingly faster, and stars would last for maybe decades or hundreds of years, but not millions of years. Obviously, in this case, you don't have deuterium, so there's no question of even thinking about carbon or oxygen. Another example, more at the molecular level, the proton to electron mass ratio, which I'm going to call mu, which is about 1,836 in our universe, it cannot be too large. If it was a lot larger, then you would not have molecular structures, for example. You would not have molecules. Still have atoms, but not molecules. So these are just small examples. You could think of several others to illustrate how the values of these constants are relevant. And since I mentioned the proton to electron mass ratio, let me make another theoretical point that we'll discuss in an observational context a little bit later on. And this relates to something that I also said yesterday. When if you have a new degree of freedom in your theory that modifies the observational consequences in some way, you should see signatures in several other ways. So one example that I want to emphasize here is that in any theory where you have a dynamical scalar field giving you a variation of alpha, a variation of Fine-Schreiber constant, you also expect the proton to electron mass ratio to vary. And the somewhat technical reason for this is that at least if you think of grand unified theories or broad class of theories in particle physics, the variation of alpha is related to the variation of the QCD scale. And this means that nucleon masses will vary if you compare them to some other mass which doesn't depend on QCD, like the electron mass. So in any theory where alpha varies, you should also expect mu to vary at some level. You can fine-tune things if you want to suppress this variation, but natural expectation is that it's there. And varying mu you can measure using molecules. Molecular hydrogen is the simplest example. This was pointed out in the 1970s, but other molecules can be used as well, and we'll see a couple of examples later on. Another example of something that also changes if you vary alpha is the temperature redshift relation. So If you assume adiabatic expansion and photon number conservations, the temperature of the cosmic microwave background goes as the inverse of the scale factor. And so this is a prediction of the standard model. Um, but this relation will change if also is varying. And a further example is the distance duality relation. So the relation between luminosity distance and the angular diameter distance, sometimes known as the Etherington relation, this will also change. So it's important to note that these variations and the way these relations change with respect to the standard model is highly model dependent. So there's some models where alpha varies very little, but the distance duality relation is changed by a lot. There's other models where the opposite happens. So the relation is model dependent. But within a given model, all these relations are fixed and are calculable. So if you have a specific model that gives you some dependence of alpha on the redshift, then within that model, and only for that model, you can in principle calculate rigorously how all the other quantities will vary. And then this allows you to observationally test these things and test whether or not this model is correct, because if you detect an alpha variation within that model, you are able to predict how the CMB temperature should change or how the distance duality should change and so on. So this is the point of consistency tests that I mentioned yesterday. Um, Another point that I want to connect to our discussion yesterday is this issue of uh, the difference between inertial and gravitational masses. So when we measure the proton to electron mass ratio, so when we measure mu, um, what we're measuring are inertial masses, not gravitational masses. And I said a minute or two ago that you can measure this proton to electron mass ratio using molecular hydrogen, or you can do it with other molecules. Now, here there's a subtle point, but also a very interesting one. If you measure mu using molecular hydrogen, you are really measuring the proton mass divided by the electron mass. If you're doing the analogous measurement using more complicated molecules, so molecules that have protons and neutrons in their nuclei, you're not measuring exactly MP over ME. What you're measuring is an effective nucleon mass divided by the electron mass. And in principle, this is the same as MP over ME, only if there is no composition dependent force. In other words, if nature treats for this purpose protons and neutrons in the same way. Now, in many extensions of the standard model, you do have forces that depend on the composition of the object. So forces that couple differently to protons and neutrons. And if that is the case, then by using other molecules to measure mu, you're not really measuring MP over ME. However, this is not a curse. This is a blessing. And it's a blessing because it allows you another test. So if you have an astrophysical system, some gas cloud with several different molecules, and you can measure this ratio in the same cloud using different molecules. So on one hand, using molecular hydrogen, on the other hand, using, for example, carbon monoxide, or in the radio band, maybe ammonia, methanol, or other molecules, then essentially you're testing composition-dependent forces. You're constraining composition-dependent forces in an astrophysical system. So to give you a mental image, so you all probably heard that Galileo once went to the top of the Pisa Tower and dropped two objects to prove that they fall at the same rate, and therefore that Aristotelian physics was not correct. Well, this astrophysical test of composition dependent forces would be the equivalent of someone going to the top of the Pisa Tower, dropping one proton and one neutron, and checking whether they fall at the same rate or not. So conceptually, this is a crucial test. It's an extremely interesting test. Obviously, you need astrophysical systems where you can see these molecules and where you can these measurements, sufficient precision and accuracy. Uh, but this test has not been done so far, but it's something that the ELT could potentially do in the future, and this is something that I'm personally quite excited about it because it's a really nice test if one can do. Okay, so the point I'm emphasizing here, and this is the last slide before we get to more observational things, is that there's a wide range of possible relations between all these observables. Um, so if you change something with respect to the standard model, you should see these effects, you should see these deviations in several different ways and in several different observables. Um, and this enables you in principle to do these consistency tests, and if and when we find evidence for this new physics, then we need to find it in several different places, and all these things are important things to look at. Now, there's a whole lot of models that we can discuss, and we'll see some examples tomorrow. Um, but for a few things that I want to discuss, there is a broad class of unification scenarios, which is convenient because it's a very broad class, but you only need a relatively small number of free parameters to characterize it. Um, so in this class of models where you assume that unification of three forces of particle physics occurs at some high energy, you can express relative variations of various quantities as a function of the variation of alpha. So to give a specific example, so if you look on the left part of the slide, you can express the relative variation of mu, the proton to electron mass ratio. So you can relate it to the relative variation of alpha using just two parameters. So these parameters R and S are numbers. And R comes essentially from quantum chromodynamics, and S comes from electronic physics. And in different unification models, these numbers will be different. But for a given model, they are numbers, and in principle, they are calculable. So in principle, this is useful because it allows you to phenomenologically study a whole lot of unification scenarios. Because every pair of values of R and S, in principle, represents phenomenologically one unification scenario. So instead of choosing one particular scenario, you can just treat R and S as free parameters and use them to express variations of other quantities as a function of those parameters and the variation of alpha. So this is an example for mu, the proton to electron mass ratio. On the right, you have the analogous relations for relative variations of the gyromagnetic ratio of the proton and the neutron. You can also express them as a function of variation of alpha. And again, they only depend on R and S. So these coefficients are calculable in these unification scenarios. You don't need to know how to calculate them for the purpose of these lectures, but you can look it up later if you want. So in purely theoretical terms, not all astrophysical targets are useful to do these measurements. Of course, we do the measurements where we can do them, where there's astrophysical sources which are suitable to these measurements. But if there are several possible choices, so several possible astrophysical targets that can be measured, and we have a limited amount of telescope time, then in addition to other criteria like the brightness of the target and how high it is on the sky and various other things, there's also theoretical considerations to keep in mind, because in some of these targets, they might be more suitable for doing some of these consistency tests. So, for example, in some targets, you can simultaneously measure the proton to electron mass ratio and the CMB temperature. If you can do both tests in the same system, that's useful. Occasionally, you can actually measure alpha, mu, and J.P, the proton to electron mass ratio, in the same target. Those are quite uncommon, and there's basically one or two examples, and they don't allow you very stringent measurements of the tree. Finding targets like this that allow you this consistency test is useful from a conceptual point of view. Now, I said we don't know what these couplings are. We don't know what role they play in our physical theories. So basically, if you want to understand why they have the values they have, or whether they're really constant or not, um, there's only two possible approaches you can follow. The first one is what I would call numerology, and this is illustrated in this paper. I'll give you a few seconds to read it, and I should emphasize that this is not the abstract of the paper. This is the complete paper. It was published in Physical Review. And I think it shows two things. So first, it shows that one can publish pretty much anything. Um, but second, I think we can all agree that this is not a satisfactory explanation for this value, right? So one needs to do a little bit more than this. And by the way, this paper, last time I checked, has I think around 20 citations. Of course, some people cite it as a joke, but still, there's a lot of papers that have less than 20 citations. So this is not a okay. So our other alternative is to actually measure these things. And so let's go back to this cartoon that I showed already yesterday. So how do we measure alpha, the fine structure constant, along the line of sight of a bright quasar? So as I emphasized, we're not going to measure alpha at the quasar. We're going to measure it at some low density absorption cloud that happens to be along the line of sight. So in this spectrum, you see a bunch of absorption lines, so red words of Lyman alpha forests, magnesium, iron, calcium, silicon, zinc, etc. And you know the wavelength of these transitions in the lab. People can measure these wavelengths in the lab. Now, when you look at them in an astrophysical system, all these absorption lines are going to be shifted to the red just because the universe is expanding. If, in addition, the strength of electromagnetism was slightly different in these absorption clouds, each of these lines is going to get an additional shift, which might be to the red or to the blue, depending on the value of alpha, whether it was larger or smaller, and depending also on the atomic structure of the atom or ion in question. Now, if you could only measure one line, these two effects would be completely degenerate, because how much a line is shifted to the red is what gives you the distance. It's the redshift. So if you just measure the position of one line, you have one measurement, and you have two uncertainties, the redshift and the value of alpha, and you cannot tell anything. But if you can measure so the position of two different absorption lines, which have different sensitivities to the value of alpha, so maybe one shifts to the red if alpha increases while the other one shifts to the blue, or one shifts a lot and the other one shifts a little. So if you can measure the wavelengths of these two lines in your absorption spectrum, and if you're sure that the two absorptions come from the same absorption cloud, so they come from the same distance from you, then you have two equations and two unknowns, and you can solve the system. Because you measure the two wavelengths and you determine the value of alpha at that cloud and the redshift of the cloud. So conceptually, this is how you do it. In practice, you don't use just two absorption lines. You use all the absorption lines that you can see in your spectrum that are not blended with other lines and so on, and for which you know accurately enough the wavelength of that transition in the lab and how much you expect the line to shift for a given variation of alpha. So this is what we call the sensitivity coefficient. So how sensitive is the position of each line to the value of alpha? And some transitions are more sensitive to the value of alpha than others. So as a rule of thumb, heavier elements are more sensitive to the value of alpha than lighter elements. So if we compare transitions of iron with transitions from magnesium, the iron lines will shift a lot, the magnesium lines will shift a lot less. I'll show you a plot in a few minutes to illustrate this. So conceptually, this is how it's done. Um, and you can do these comparisons in several different ways. And depending on the pairs of transitions that you measure, you're going to have sensitivities to different quantities. So for alpha, for example, to measure directly alpha, you can compare fine structure doublets. To measure mu, the proton to electron mass ratio, use molecules. You can use molecular rotational or vibrational transitions. Typically in the radio band, you cannot measure alpha or mu directly and in an isolated way, but you can measure combinations of alpha, mu, and the proton to electromagnetic ratio, J.P. So various different combinations. So you can you measure what you can depending on what transitions you see in your astrophysical system. But in principle, there's several different ways of doing these measurements. When it comes to alpha, it's actually simpler to do measurements using emission lines than using absorption lines. Nevertheless, measurements with emission lines are a lot less sensitive than the absorption lines. People have done this with Sloan data, for example, so doing a measurement in emission, so using the O3 lines, for example, and you gain some. You have a statistical gain because you have lots and lots and lots of galaxies, but still you do not have the sensitivity that the high resolution spectroscopy and absorption gives you. Now the state of the art in the field these days is given by Espresso, but let me, before getting to Espresso, summarize a little bit the state before Espresso. So there were close to 400 different measurements of alpha and other quantities, mu or combinations of alpha, mu, and J.P. This doesn't mean 400 lines of sight because sometimes you have several different absorption clouds in the same line of sight and you can do several different measurements of alpha. And if you do a kind of agnostic likelihood analysis, if you just take all the measurements at face value with the error bars as given by each original paper, you can do a joint likelihood analysis to extract the best fit values of alpha, mu, and J.P. So remember that in some cases you measure alpha or mu individually, but in other cases you only measure a combination of alpha, mu, and J.P. But nevertheless, you can put all the data together in a single likelihood. And there what you find is that there is no strong evidence for variations, that there's a 1 to 2 sigma preference for non-zero values of the relative variations. And this is true whether or not we have an archival data set by John Webb and his collaborators, which, as you might have heard, has suggested variation for alpha, which I'll come to in a minute. So in these three plots, what you see are 1, 2, and 3 sigma contours in each of these planes. So on the left, I have delta mu over mu versus delta J.P. over J.P., and then the other two combinations. So these are all relative variations with respect to the present day value, so the lab value, and they're always expressed in parts per million, so units of 10 to the minus 6. And for convenience, I've separated the data set into two subsets. So the red contours are for data below redshift 1, the blue contours are for data above redshift 1, and black is just a combination of everything. This division at redshift 1 is to some extent arbitrary, but in the case of mu, it makes a bit of sense because you can do measurements of mu in the radio band below redshift 1, and in the optical, so visible band, you can only do them above redshift 2. So at least for mu, this division is is justifiable. So that there is no strong preference for variation, even at statistical level, but it's also known that all pre-espresso spectrographs have systematic uncertainties having to do with intra-order and long-range distortions of the spectrograph at the level of 3 parts per million. So this is a number to define. Now, Webb and collaborators have suggested a while ago that there's actually a statistical preference for a spatial dipole on the sky, meaning if you look in some direction, there's a slight preference for a larger value of alpha, so for a stronger electromagnetic interaction, whereas if you look in the opposite direction, there is the opposite preference, so a weaker electromagnetism. And in pure statistical terms, the significance is a bit over 4 sigma, or at least it was in 2011 when they published the original data set. And I emphasize that all of this is archival data. It is data that was not taken for this purpose, was sitting in the ESO archive or in the Keck data archive, and it was reanalyzed for this purpose. And this is an important point here, because whenever you want to do these measurements, you have to be extremely careful with the way you calibrate data. And there's calibration procedures, which in principle you can only do properly if you take this calibration data at the same time as you take your quasar spectrum. You cannot calibrate it a posteriori because the spectrograph might change, the temperature and pressure conditions during the observations can change, all of that can change. So it's difficult to correct a posteriori. So a more recent analysis I've done with a former student, so combining the Webb data with more recent data, still pre-espresso, lowers the statistical significance to about 2.3 sigma. And again, this is only a statistical analysis. It disregards the possible systematic effects. So on the left, you see the distribution of these measurements on the sky. So right ascension versus declination. So the gray band is the galactic plane. So there's no measurements there for obvious reasons. And you can see that there's a lot of scatter, but more or less by eye, you can see a slight preference for larger values in one part of the sky and smaller values in one part of the sky. Now you can also do another test, which is, so you fit for the direction of the dipole of alpha on the sky, and this is what the plot on the bottom right shows you. So here, my sky is rectangular, so I have right ascension on the horizontal axis and declination on the vertical axis. And the red contours show the 1, 2, and 3 sigma constraints on the direction of the north pole of the alpha dipole. Solid and dashed lines are for slightly different assumptions, but we don't need to worry about that. So this is the preferred direction on the sky of the alpha dipole. Now, as we said a few moments ago, if alpha varies, you should also expect mu to vary. So there's also measurements of mu, and you can also search for a dipole in mu. So in this case, there is no statistically significant reference for one. There's an upper limit, but you can still constrain the best fit direction of this hypothetical mu dipole on the sky. And the argument is, if this alpha variation is real, and if there's also a mu dipole, then you expect the two dipoles to be aligned on the sky, because presumably they come from the same physics. But actually, when you do the analysis, the best fit mu dipole, so that is given by the blue contours, is actually in a different direction on the sky by quite a lot than the alpha dipole. So this is, again, another way of saying that there is no statistically significant reference for this dipole on the sky. So usually these measurements are done in the optical or in the radio band, but you can also do them in the infrared. So there's at least 4 measurements of alpha in the infrared. So this is something that I was part of a couple of years ago. So for some high redshift quasars, you can actually see some of the transitions that are useful for measuring alpha. So in particular, there's this quasar J1120 plus 0641. It's a redshift slightly above 7, but it has some absorption clouds starting at redshift 5.5 approximately. And this actually enables a measurement of alpha. So this is data that comes from 30 hours with the extra spectrograph, much lower resolution than UVs or IRIS at keck. But still, as a proof of principle, it allows you a measurement of alpha. And you see on the bottom left the various absorbers that are along the line of sight of this quasar. So the 4 highlighted ones in bold are the ones that we use for the measurement, and the bold phase transitions are the ones used for the measurement itself. So you combine constraints from all these transitions to get the measurement, and this is summarized here. So this table has all the pre-espresso direct measurements of alpha. So everything up to redshift 4 was done in the optical, so mainly with UVs at the VLT or IRIS at keck. There's a few measurements from Subaru as well. And in the higher, so in the right part of the diagram, you see these measurements in the infrared. So the gray ones are the 4 individual ones. The black one is the weighted mean of the 4. Obviously, the error bars are much bigger than the optical ones. So the optical error bars are at, let's say, few parts per million or tens of parts per million. Here we are at 100 parts per million or a bit more. So in that sense, the measurements are not really competitive with the low redshift ones, but they are area redshift measurement, and this is a proof of principle to show that one can actually do these measurements in the infrared. Of course, there's other things to worry about. There's telluric lines and various other things. But in principle, we can push these measurements to higher redshifts with VLT, for example. Okay, but then espresso comes along, and so the background that you've been seeing is actually what espresso looks like in the combined CUDE lab of the VLT. So the spectrograph itself is inside this vacuum vessel. So it's a thermally and so the environment is stable in terms of temperature and pressure, which is a big advantage as compared to earlier spectrographs. Another interesting feature of espresso is that it can take light from one of the unit telescopes of VLT, or it can take light from the 4 of them. You combine lighting coherently from the 4 and feed it the spectrograph, and that gives you effectively a 16-meter diameter telescope. And the bit you see here on the bottom and left part of the image is this. Is the end of the CUDE train, so the part that combines the light of the 4 telescopes. So you can choose which telescope you use to feed light to espresso, and that could be one telescope or it could be the 4 of them. So here's some specs of the instrument. So this might not be particularly relevant for most of you, but just to show that espresso has several modes with different resolution, both for 1 UT and for the case of the 4 UT, so when you combine the light coherently. So the wavelength range is from about 0.38 to about 0.79 micron. And of course, depending on the science you want to do, you're going to use one or more of these modes. So in some cases, it's not obvious which of the modes is the ideal one for you. And as is the case with these instruments, so the consortium of which we are part, built the instrument, provided espresso, to ESO, which in turn provides it community, and in return we get some nights of guaranteed time observations. So Espresso is basically two science cases. One is exoplanets, the other one is fundamental physics. So this slide summarizes our plans for the GTO. So this includes direct measurements of alpha using various ions and various possible lines of sight. Direct measurements of the proton to electron mass ratio. Espresso is not sufficiently blue; it doesn't have enough blue coverage to do a lot of these measurements, but it can maybe do a couple of them. Direct measurements of the CFP temperature. I'll come back to those a bit. Also, you can do measurements of deuterium, so the primordial deuterium abundance. It can do a pilot test of the redshift drift that I'll discuss later in the week. And we also have some ideas for additional things, so taking a very deep spectrum, looking at lensed quasars, and so on. So the first data, the first measurements of alpha was taken in November 2018. So this is Anna Katerina Leit, my former PhD student, who went to Paranal to do the observations. Then, of course, COVID came along and the observatory shut down and that. So this has delayed us by quite a bit. But eventually we got to the first published measurement of alpha from Espresso. This is a paper led by Michael Murphy, and it relies on a detailed analysis of the Espresso calibration pipeline led by Tobias Schmidt. So this is a measurement of alpha along line of sight of HEO 515 minus 44. It's a very bright quasar, which has an absorption system at redshift of 1.15, and it's kind of the go-to quasar for these measurements. It's a measurement based on 16 hours of data, and we've also done a blinded analysis of the spectrum, which is a sort of novelty in this field. And the result is what you see in the little white box. Delta alpha over alpha, again, relative variation, alpha then minus alpha now divided by alpha now is 1.3 parts per million, plus or minus 1.3 statistical uncertainty, plus or minus 0.4 systematic uncertainty. So it's consistent with no variation. It's also consistent with the dipole because it's basically along the equator of the dipole, so you don't expect that much variation there. And the number might not seem, hugely exciting to you, but I should emphasize that this is the most accurate constraint to date, and it's one of the most precise. And it's certainly the first time that the systematic uncertainty is clearly smaller than the statistical uncertainty. So here we're limited by photons, not by systematics of the calibration or something like that. So this is new in the field. In the bottom right, you see a bit of the error budget of this analysis. It's slightly technical, so you don't need to worry about it too much. But those of you with a stronger interest in spectroscopy can see what kinds of things we worry about. In the bottom left, you can see some illustrations of the sensitivity coefficients I mentioned earlier. So this is the rest wavelength of each transition, so the wavelength in the lab. And in the vertical axis, you have the sensitivity coefficient, so how much a line shifts for a given variation of alpha. And you see that some transitions have a positive sensitivity coefficient, some have a negative sensitivity coefficient. Magnesium transitions, so magnesium is very light, have a sensitivity that is almost zero. So this is what I said earlier. You compare lines that shift a lot with lines that almost don't shift. And these lines that don't shift is what we call anchors. Because since they are insensitive to the variation of alpha, they're a good way to pin down the redshift of the absorption power. Of course, in practice, you do it with a robust, sophisticated analysis, but the bigger the range of sensitivity coefficients you have, the transitions that you see, the more sensitive you will be, so the better will be your constraint. Um, just for illustration, so this is a way to showcase the high resolution of the espresso spectrograph. It also shows that this is a very complicated absorber. It's not a one monolithic cloud. There's lots of structure. And in the top part, you compare a narrow region of the spectrum. So you're comparing espresso with UVs. There's three different transitions. So two magnesium transitions, one iron. They're just being offset for the sake of visibility. In the bottom part, you compare espresso with harps. Again, same region of the spectrum, and you see the spectra are broadly consistent as you'd expect, but there are small differences, and these small differences actually translate to different sensitivities to the value of alpha. So one of the bottlenecks of espresso is the lack of coverage in the blue. This is also relevant for the LT, for Andes, for example. What this diagram shows is for various transitions that are used for the measurement of alpha, which are plotted along the vertical axis, the range of redshifts in which the VLT, so UVs, can see these transitions. So that's the thin line. And the same range for the espresso spectrograph. So that's the thicker line, which clearly is a much smaller one. The color denotes the sensitivity coefficient. Basically tells you which lines shift to the red, which ones shift to the blue for a given variation of alpha. And the lines that are dashed are essentially lines of magnesium in silicon, which are the anchors I mentioned a minute ago. So they are the lines that shift very little. So they're used to pin down the redshift. So as a back of envelope rule, in order to get a good measurement of alpha, you'd need an absorption system in which you see some anchors, some lines that shift to the red, and some lines that shift to the blue. Sometimes you don't have all three of these, but if you can get all three of them, that's okay, let me mention other ways to measure alpha. So I don't have time to cover all these in detail. I'm happy to discuss them later on, but I just want you to get an idea that this is a very active field and lots of things are happening. So you can do these measurements in the lab using atomic clocks. So you can take two atomic clocks based on two different transitions with different sensitivities to alpha, put the two clocks on the lab side by side, see if they run at the same rate or not for a few months, maybe a couple of years. And essentially that constrains the rate of change of alpha. So alpha dot over alpha. In other words, 1 over alpha d alpha dt. So it's the rate of change today. And you get extremely sensitive constraints at the level of 10 to the minus 19 per year. So this is a rate of change. It's extremely strong. And the prospects for improving it are good. People think they can build nuclear clocks with sensitivities of 10 to the minus 21. So improve these constraints by a factor of 100. There are several astrophysical objects, compact objects, that can be used to constrain alpha. In particular, to constrain environmental dependencies. In other words, whether alpha depends on the local gravitational field or local density. Here, the limiting factor typically is nuclear physics uncertainties. But this has been studied for population tree stars, for solar type stars, for neutron stars, for white dwarfs, etc. And in fact, you can actually measure the value of alpha and the value of mu in the atmosphere of white dwarfs using highly excited ions. More recently, Michael Murphy and his collaborators have started a very interesting project using solar twins to constrain the value of alpha in different positions of the galaxy and to check whether there's a coupling with the dark matter. So, as you know, the dark matter distribution changes with the distance to the center of our galaxy. So if you can measure alpha at different distances from the galactic center, you can, in principle, constrain these kinds of couplings. And again, the sensitivities are extremely good, but better than parts per million, and there's prospects to improve them even more. Then people talk a lot about Oklo. So Oklo is a natural nuclear reactor that went off in Gabon, in Africa, about 1.8 billion years ago. Nominally, this gives you a constraint on the relative value of alpha, delta over alpha, at a level of 10 to the minus 8, which is much stronger than quasar measurements, which are at 10 to the minus 6 level. On the other hand, this is not a clean measurement, and it's only a measurement or a constraint of alpha if you assume that alpha is varying, but everything else is the same in the standard model. And of course, that's a very simplistic assumption. A more realistic way of thinking of Oklo is actually as a constraint on the strong nuclear coupling, alpha strong. So be a bit careful on whether or not you use Oklo for combining it with other constraints, because it has a very strong assumption behind it. You can also get constraints from other contexts using cosmic microwave background, Big Bang nucleosynthesis, Tsuniav-Zeldovich effect with clusters of galaxies. Typically, these are weak constraints at percent level, maybe 10 to minus 3 level, essentially because there are degeneracies with various cosmological parameters. Although you can improve constraints a little bit if you choose specific models. But then, these will not be model independent constraints, they'll be constraints for a specific model. And just to illustrate a little bit how this happens, if we take the CMB, well, if you change alpha, then you're going to change the ionization history of the universe. All the energy levels, all binding energies, etc., will be shifted. The Thomson cross-section will change because that depends on alpha squared. And in the bottom left, you can see an illustration of how the angular power spectrum of the CMB would change if you change alpha by 5% one way or the other. In other words, if you increase it or decrease it by 5%. So the position and the amplitude of the first peak and also the secondary peaks gets changed a little bit. The silk damping tail is also affected. So a 5% variation is visible on the CMB, but you cannot go much further than 0.1% constraint or something like that because you hit various degeneracies. For Big Bang nucleosynthesis, so in principle, this has the advantage of being much higher redshift. On the other hand, you cannot get a model-independent constraint. Essentially, you fail at the first hurdle because there's no model-independent way of describing the difference between the neutron and proton masses, and that's the first thing that will affect the BBN outcome. The typical thing that people do is to assume something like the Gasser-Leutwiler formula, but by more or less unavoidably, this will be a model-dependent constraint. And again, on the right, you see the typical BBN plot with the abundances as a function of the variant to photon ratio, and you see the effect of a 5% change of alpha at the BBN epoch. And of course, in both of these, we're assuming that alpha is the only thing that is varying and everything else is kept unchanged, which again is a somewhat simplistic assumption. You can actually do better analysis than that. This has been done for BBN, not for the CMB. So yeah, all these constraints, they're interesting constraints, but they're not at the same level of precision and accuracy as the quasar constraints, and in any case, they're weaker constraints. So there's no physically realistic model that I know of that satisfies quasar constraints, but which could be ruled out by CMB constraints, for example. So any model that satisfies quasar constraints and atomic clock constraints also satisfies current CMB constraints. Okay, so I think this is a convenient place to stop for today. We'll continue tomorrow. So let me stop sharing my screen, and I'm happy to take questions.
Perfect. Thank you, Professor. Questions? One here.
Mm, you can see me, you can hear me.
Yes.
Nice talk. Thank you very much. I have one question. You can show us, for example, the implication of this variation in the fundamental constants, for example, a level of molecular and nuclear interactions, for example. But I think that, for example, it's well known that from the quantum physics, these constants speed of light and alpha are related. And I think that which are the consequences? For example, if you vary the fine structure constant, and I have a variation, for example, in the speed of light at level of fundamental physics.
Okay. So the answer is it doesn't matter at all. Anything that you can measure in physics is a dimensionless number, right? And alpha is a dimensionless number, so I can measure it, and it's a number, and it's the same in any system of units and so on. The speed of light or the electric charge have units, so those depend on the choice, but that choice is not unique. In other words, let me maybe explain it with a specific example. So let's say that one finds that alpha varies and it's some function of redshift. Right? We measure alpha at various redshifts and find some alpha as a function of redshift, which we describe by some scalar fluid model, etc. Now, given that alpha variation, that alpha of z, uh, you can find one model where the electric charge varies. So you can essentially translate that variation of alpha into a model where the electric charge depends on redshift, but Planck's constant and the speed of light don't. So that's one possible model. It essentially corresponds to one choice of units, one choice of unit of length and a unit of time and a unit of energy. But equally, someone can take that alpha variation, that alpha of z, and by making a different choice of units of length, time, and energy, rephrase it as a model where the speed of light varies and the electron charge is constant. And observationally, the two models, so the model where the speed of light varies and the electron charge varies, are exactly identical. There is no test that you can ever make, even in principle, that will separate the two. Because the only thing you can measure are numbers, dimensionless quantities, and those, in this case, would be the fine structure constant, which by construction, in the example I've given, is the same. So both models have the same alpha of z, even though one is a varying c and the other one is a varying e. But observationally, they are exactly identical. Because any measurement you make in any physics lab or in any astrophysical system is a number, right? And that number cannot depend on the choice of units that you make. When you translate this into a particular model, then you make a choice of units. But the measurement itself is dimensions.
Thank you very much.
Adele?
First of all, thank you very much for the very nice talk. And I have a question and a comment. The question would be if you know if there are now ongoing projects for measuring alpha from where the possible variation in alpha from white dwarfs.
Not that I'm aware of. So people have done so the measurements I mentioned come from data from the Hubble Space Telescope, which is it allows you to do the measurements, but it's not really good in terms of calibration of the data. So and there are several things that you'd like to do to calibrate data and which you can do on the ground that Hubble Space Telescope doesn't allow you to do. So there we're a little bit stuck, let's say, because James Webb doesn't see the blue part of the spectrum, which is where we'd like to do this measurement. So maybe with next generation space telescope that NASA is now planning, so that should have optical coverage. It should go into the blue, and presumably that would be a good facility to do these measurements. But that's maybe 10 or 20 years in the future. For the Hubble telescope, I guess people could apply for more time and do more measurements. I'm not aware of anyone doing them. I'm not doing it myself. I think the limiting factors would be the same, and maybe people realize reading the papers that you're not going to gain that much because the white dwarfs that have been observed are more or less the ones that people expect to give you the best measurements anyway.
Okay, and the comment would be about the CMB measurements of the variation in alpha. You commented that the level of variation that you can measure are more or less than the case of the quasars, but I would like to point out that these kind of measurements from the CMB are interesting because, for example, if you consider the variation in the electron mass, you get a value of the Hubble constant that helps you to mitigate the Hubble tension, which is very important in cosmology. So maybe the level of variation is not that important, but these measurements are important for other important things in cosmology.
Sure. That's fine. I'm only so for the purposes of these lectures, my focus is to use these measurements as a direct test of models or classes of models, and in that sense, I think so. What I said is true. So there is no model that satisfies quasar data that would be ruled out by CMB data. So as a discriminating test between models in this specific sense, they're not competitive. But what you said is correct. They are useful probes of new physics in a broader context, certainly.
Of course, thank you very much.
Okay, more questions? Nope. Well, let's thank him again.
Thank you. So again, feel free to ask questions on Discord if you have them, and if not, I will see you again tomorrow.
Okay, see you.
See you.